Section 5.10. There is no second best. Air power is like poker. A second best hand is like none at all. It'll cost you dough and win you nothing. General George Kenney. Section 5.10.1. Physical cost function protocols can't be replicated by ordinary computers or software. Another reason why it is so important to point out what's going on under the hood with physical cost function protocols like Bitcoin is to illustrate how there are very meaningful physical differences between this technology and other computer programs. People who utilize proof-of-work protocols like Bitcoin are technically using a different style of abstract thinking than people who utilize regular computer programs. Without examining the underlying tech stack, it is impossible to see these differences, or to appreciate how the abstractions used to describe objects like bitcoins have different complex emergent properties that are physically impossible to reproduce using regular computers. When operating ordinary computer programs, people assign meaning, for example Boolean logic, to transistor state changes in a state machine. However, when operating physical cost function protocols, aka proof-of-work protocols, like Bitcoin, people also assign abstract meaning to quantities of physical power, as illustrated in Figure 82. Illustration of physical and systemic differences between technologies. This means the abstractions people use to describe the complex emergent behavior of ordinary programs are both physically and systemically different than abstractions used to describe proof-of-power systems like Bitcoin, even though they have the exact same semantic specifications. The bits produced by normal software using normal computers have physically and systemically different properties, which means the abstractions used to describe those bits also have physically and systemically different properties, even though we give them the same name. It is physically impossible for a coin generated by an ordinary computer program to have the same complex emergent properties as a coin generated by a proof-of-work protocol like Bitcoin, because they are physically different systems. In the same way that something which doesn't physically exist doesn't have the same complex emergent properties as something which does physically exist, particularly properties like being verifiably scarce or decentralized, bits of a coin created by an ordinary piece of software running on an ordinary computer can't have the same complex emergent properties as Bitcoin. From the software at the top of the tech stack all the way down to the underlying state mechanism, Bitcoin is a fundamentally different computing system with physically different and reverse-optimized hardware, making it incomparable to traditional computing systems. When people normally refer to an object instantiated by ordinary software, they are applying abstract and symbolic meaning to transistor state changes inside a computer using machine code to convert them to machine-readable bits of information. These objects do not physically exist. People have arbitrarily chosen to describe the complex emergent behavior of their computer programs using metaphors like objects. For example, folder, trash can, cloud, and string, to make it easier for other people to understand the intended functionality and design of their computer programs. In other words, there is no spoon. All that physically exists is the physically unrestricted and infinitely expanding state space of countless state machines plugged together. Countless transistors are added together on circuit boards, and the combined state of those transistors is what we abstract as so-called objects. But underneath the metaphor is nothing but people converting transistor state changes to bits of information using a new type of symbolically and syntactically complex language. Physical cost function protocols, aka proof-of-work protocols, like Bitcoin, work differently. When people describe the real-world physical cost of solving a physical cost function protocol as if it were a quantifiable object, for example, a proof, receipt, stamp, coin, or token, they're using abstractions to describe a real, meaningful, physically scarce, physically constrained, thermodynamically restricted, path-dependent, and irrevocable quantity of physical power drawn out of shared, objective, physical reality. Therefore, whereas ordinary computer programs can only present the illusion of physical cost function protocols like Bitcoin produce real-world physical cost. Whereas ordinary computer programs can only present the illusion of scarcity and decentralization, Bitcoin produces real-world scarcity and decentralization. This is possible because the underlying physical state-changing mechanism, in other words, massive quantities of watts, being converted into bits is itself physically real, physically scarce, and physically decentralized. You know that bits of information created by large quantities of physical power are real, scarce, and decentralized because power itself is real, scarce, and decentralized. The physically costly quantities of real-world power utilized by protocols like Bitcoin double as machine-readable bits of information, which are then described as abstract objects like coin. Combining these concepts together, we can see there's a substantial difference between the abstract objects produced by regular software and the objects produced by physical cost functions, aka proof-of-work protocols, because the bits we arbitrarily call objects are derived from physically different and reverse-optimized phenomena. These differences go undetected because most people aren't paying attention to the underlying state mechanism. They're only paying attention to the software layer, where everything looks the same because we're using the same metaphors, not the hardware layer, where it's incontrovertibly true that there are meaningful physical differences. The same object-oriented software abstractions refer to two completely different physical phenomena with completely different physical and emergent properties. As discussed in the previous section, the bits produced by ordinary computer programs have the exact opposite design intent as the bits produced by physical cost function protocols. Right now, people are treating these bits as if they're the same thing, without taking the time to understand how these bits have been intentionally reverse optimized. One explanation for why computer scientists and software engineers keep overlooking these differences is because they've become accustomed to evaluating tech stacks from the top down, not the bottom up. So naturally, they aren't going to detect that a new state mechanism has been added to the bottom of the Internet's tech stack. It would appear that software engineering culture has become so accustomed to abstraction, information hiding, and ignoring everything below assembly language that they don't recognize how proof of work utilizes a completely different state mechanism with properties that are physically impossible for non-proof of work systems to replicate. This concept is illustrated in Figure 83, illustrating the physical differences between different technologies. Physical cost function protocols, aka proof of work protocols, are deceptively simple. They convert watts to bits. When people utilize computing networks like the Bitcoin network, they take watts as their input and convert them into proofs of watts as their output, which are then metaphorically described as some type of abstract object. Lost in the metaphors, computer and software engineers aren't taking the time to consider the major technical differences in the underlying physics, despite how observably different it is. Why do these major technical differences go undetected? The author hypothesizes that it could be because proof of work represents an unprecedented approach to computing that software engineers aren't recognizing yet, because they have effectively been trained by their industry best practices to ignore what's happening under the hood of their software by abstracting it away. As previously discussed, computer programming is an enormously complex challenge. It is essential for computer programmers to reduce cognitive distance and lighten the metacognitive burden of software engineering as much as possible. Object-oriented software design is one of the most common abstraction techniques. An easy thing to do to reduce cognitive distance is to call the proof of power receipt produced by a physical cost function a receipt or stamp or token or coin, and then to simply move on without taking the time to sort through the physical details. When computer scientists and software engineers do this, they tacitly treat the abstract object produced by a proof-of-work protocol, for example a Bitcoin, as if it were the same as any other abstract object produced by software, despite obvious physical differences in the underlying tech stack. Consequently, they miss the fact that Bitcoins are physically costly, constrained, and decentralized in a way that no ordinary software object can be. Probably the most famous example of people making this mistake is when they claim that proof-of-stake protocols can have the same complex emergent properties, for example, decentralization, as proof-of-work protocols. What these people are overlooking is the fact that stake and work are physically incomparable, because stake refers to an ordinary software abstraction for a normal computing system, whereas work refers to a software abstraction for a fundamentally different type of computer, with a fundamentally different type of underlying state machine. More on this in the following sections. Using abstractions like Bitcoin, critical information about the differences in underlying physical hardware is lost, in the same way that critical information about the underlying physical hardware of the cloud is lost. As previously discussed, this is a recurring challenge of software engineering that negatively impacts security. The semantic ambiguity of software specifications is a well-known problem in cybersecurity that causes people to overlook vitally important security information, like how storing sensitive information on the cloud really just means storing sensitive information on someone else's computer that you can't control, that belongs to somebody you must trust. Just like the term cloud hides critical information about where bits of information are being physically stored, the use of object-oriented software abstractions like COIN for proof-of-work protocols disguises the fact that the bits of information that are being metaphorically described as a coin represent state changes occurring outside of our computers, not inside of them. Because people don't understand computer theory, and they aren't paying attention to the bottom of the tech stack, they overlook highly unique properties of proof-of-work protocols, which have a potential to change the game of cybersecurity, or even change how humans perceive cyberspace. Ironically, most people have no problem recognizing Bitcoin's substantial power usage, but they struggle to understand why that substantial power usage is the irreplaceable innovation. Section 5.10.2. It is physically impossible for proof-of-stake protocols to replicate proof-of-work protocols. For what might be the first time since Neumann's invention of stored program computing techniques, people are learning to use proof-of-work protocols like Bitcoin to program something other than materially inconsequential state changes inside a state machine. The massive electric power deficits produced by protocols like Bitcoin represent physical state changes of the surrounding environment outside the boundary of our ordinary computers. This makes it possible to couple information stored as state changes inside of an ordinary stored program computer to state changes stored outside of a computer, effectively bridging the cold, hard, shared objective reality of our physically constrained and thermodynamically restricted environment to the virtual reality of cyberspace. The key takeaway is that proof-of-work protocols developed by computer engineers like Adam Back may represent the discovery of an externally stored programming technique that simultaneously changes the physical state of the environment outside of our computers, as well as the physical state of the environment inside of our computers, giving computer programmers a way to program our virtual environment and physical environment simultaneously, and then link them together. With this capability, the abstractions we use in cyberspace start to reshape our surrounding physical environment, and then import the real-world physical properties of our surrounding environment, properties like physical cost, physical scarcity, and physical decentralization, into cyberspace. It sounds extraordinary, but all it takes to achieve this is for people to simply build the infrastructure needed to convert watts into bits, which is precisely what the Bitcoin network is doing. These concepts are illustrated in Figure 84, breakdown of a proof-of-work tech stack. These theoretics emphasize the point that Bitcoin, the system, represents a physically different protocol that is disrupting the internet from the bottom up. The Bitcoin system has irreproducible, complex emergent behavior, because it uses a different base layer state mechanism that has been intentionally reverse optimized to produce more physically expensive bits rather than less physically expensive bits. This critical information about proof-of-work computing systems is hidden by the metaphors used to describe the software, which is not surprising considering how information hiding and abstraction is treated as a virtue within the field of computer science. As discussed in section 5.4.6, critical information about substantial technical differences that impact security often gets overlooked because of the arbitrary semantics used to emphasize different features of the software. Since the physical differences at the bottom of the tech stack are intentionally ignored, software engineers keep fraudulently asserting that they can replicate the same complex emergent properties, namely decentralization, of Bitcoin using regular programs running on ordinary computer hardware. Additionally, since the physical differences are grossly misunderstood, the general public will claim that Bitcoin's computing network is energy inefficient, and that it could or should be replaced by something more environmentally friendly. These misguided, or blatantly fraudulent, assertions are being made because people are missing the point, or deliberately disguising the point, that making a physically costly computer for the purpose of producing physically constrained and thermodynamically restricted bits of information is the primary value-delivered function of proof-of-work protocols like Bitcoin. The point of the protocol is to create and utilize physically expensive bits of information, as physically expensive bits are useful for cybersecurity and many other applications that we are just now beginning to discover. The software engineering culture of abstraction and information hiding explains the public misconception of proof-of-work protocols like Bitcoin. The information needed to understand the novel computer theory behind proof-of-work is lost in the metaphors we use to describe how and why it was designed. This explains why so many software engineers will claim to be able to replicate the complex emergent behavior of Bitcoin using metaphors like blockchains or cryptocurrencies that are ostensibly more energy efficient. These claims represent a gross lack of appreciation for the complex dynamics of power projection and reverse-optimized computing, perpetuating a decades-old and well-established software engineering culture of not paying attention to the physical differences of the underlying tech stack. It's incontrovertibly true that Bitcoin has a far different physical signature than these other so-called blockchains. But computer and software engineers aren't taking the time to study why it's physically different and what that means for computer theory as a whole. Probably the most famous illustration of this lack of appreciation for power projection and the novel computer theory behind proof-of-work protocols is amongst those who believe proof-of-stake protocols can replicate the same complex emergent behavior and be a more energy-efficient alternative to proof-of-work protocols. When people make these claims, they illustrate that they don't understand the primary value-delivered function of proof of work, to be physically costly. Proof of work and proof of stake are physically and systemically different technologies that utilize completely different, reverse-optimized state mechanisms that are practically incomparable, no matter what arbitrary metaphors are used to try to categorize them as the same technology. For example, blockchain or cryptocurrency. For the same reason, it's not possible to claim that something which doesn't exist is equal to something which does exist, it's not possible to claim that proof of stake is equal to proof of work. The incontrovertible difference between these two protocols is that one is far more physically expensive, in watts, than the other one. These physical differences would imply that it's physically impossible for proof of stake to have the same complex emergent properties, namely physical cost, physical scarcity, and physical decentralization, as proof of work protocols. It should be clear to any observer that the bits of information produced by a proof of stake protocol cannot replicate the physical expense of the bits of information produced by a proof of work protocol, because that difference is directly measurable in watts. Therefore, the issue isn't that proof of work is too physically expensive. The issue is that people don't understand why physically expensive bits are useful in the first place. Probably because they don't understand power projection dynamics and how physically expensive bits could be used to increase the cost of attack, thus decreasing the benefit-to-cost ratio of attack of our computing systems. In addition to not understanding why it would be useful to have physically expensive bits, the general public also doesn't seem to understand that stake is not even a real thing. It's a metaphor. Just like there is no spoon, there is no stake. The term stake is just a metaphor for the special administrative privileges given to users who own Ether, the currency unit of the Ethereum blockchain. It's a purely imaginary concept, an object-oriented software abstraction that doesn't physically exist, and therefore is physically impossible to be costly, scarce, or even verifiably decentralized. Stake, and the special administrative privileges it provides, cannot be decentralized anywhere except exclusively within people's imaginations, because stake itself is an abstract concept. Proof of stake systems are what's known as decentralized in name only, DINO, systems, because it's physically impossible to verify that stake isn't already majority owned by a single person or organization. Much more on this in the next section. Another way to conceptualize the difference between proof of work versus proof of stake systems is to borrow from the concepts of power projection theory and rename these protocols proof of real power versus proof of imaginary power. Proof of stake is proof of imaginary power, aka proof of rank. A proof of stake system is yet another form of exploitable abstract power hierarchy, where a select few people within a carefully encoded abstract power hierarchy get consolidated administrative permissions and control authority over an underlying resource. Therefore, A proof of stake, aka proof of rank or proof of imaginary power, protocol is functionally the same type of systemically exploitable, rank-based belief system as a government rule of law, complete with exactly the same type of systemically exploitable voting logic. Moreover, proof of stake is clearly a plutocratic design, where those who have the most ether can also have the largest amount of abstract power, aka stake. Because they're functionally the same type of encoded abstract power hierarchy, where a select few people control the underlying resource, that means proof of stake systems also have the same type of systemic security flaws as traditional governments and rules of law, plutocracies in particular. Additionally, because they're the same type of software running on the same type of computers, that means proof of stake systems also have the same kind of cybersecurity vulnerabilities that practically all traditional software systems have, namely the inability for users to physically, as opposed to logically, secure themselves against the systemic exploitation of encoded design logic. As proof of stake systems become more popular, the benefits to be gained by exploiting the special administrative privileges given to those who control the most stake, aka the benefit of attack, will increase, but the physical costs of attacking the system, aka the cost of attack, will continue to remain fixed at practically zero. Thus, the benefit-to-cost ratio of systemically exploiting proof-of-stake systems, aka BCRA, will gradually approach infinity as more people adopt these systems. Slashing, the confiscation of staked ether, doesn't prevent this, because the top stakers would clearly have the incentive and the means to slash users back. Moreover, slashing is a voting-based system that is endogenous to the system, meaning it can, and most assuredly will, be systemically exploited by those who encoded the design logic, which incidentally are probably the same people who control the majority supply of stake. Ironically, proof-of-stake systems recreate the exact same type of systemically exploitable, trust-based, permission-based, and inegalitarian abstract power hierarchy that it was ostensibly created to replace. Instead of creating a decentralized system, a proof-of-stake system gives unimpeachable control authority over the system to an anonymous group of people who control the most of an imaginary object called stake, which is really just another name for rank, in other words, abstract power, and administrative privileges. Instead of creating a decentralized organization, proof-of-stake systems like Ethereum have created a system that masquerades as a decentralized system, because those who control the majority supply of stake can take advantage of the disembodied nature of software to obfuscate how centralized and consolidated that stake is. To believe that proof-of-stake protocols can serve as a viable replacement to proof-of-work protocols is to believe that something which doesn't physically exist can have the same complex emergent properties as something which does physically exist. Proof of stake is yet another systemically exploitable belief system that people are adopting for what are often ideological reasons, because they desire a viable replacement for physical power as the basis for settling disputes, establishing control authority over resources, and achieving consensus on the legitimate state of ownership and chain of custody of property. Ironically, this means that proof-of-stake systems represent the exact same style of abstract power and empire building discussed in the previous chapter, complete with the exact same style of ruling class, wielding yet another type of asymmetric abstract power and control authority created by convincing a population to adopt the same belief system. To repeat the same point using the concepts introduced in section 4.5, stake is nothing more than imaginary power masquerading as real power. Watts. Like every other type of imaginary power that has ever been conjured up by people searching for a viable replacement to real power, stake is neither self-evident nor self-legitimizing. It's systemically endogenous to the software which instantiates it, making it highly vulnerable to systemic exploitation and abuse by the people who write the software. It's physically unconstrained and thermodynamically unsound, bounded, zero-sum, non-inclusive, inegalitarian, and non-attributable. This makes proof-of-stake protocols physically and systemically opposite from proof-of-work protocols. To believe that two physically and systemically opposing technologies can achieve the same emergent effect is equally as silly as the concepts presented in the previous chapter, where people believe that a man wearing a wig has the same type of power and can achieve the same type of security as a woman firing the Gatling gun of an A-10 Thunderbolt II. This concept is illustrated in Figure 85. Illustration of the difference between proof-of-work and proof-of-stake protocols. To persuade people that proof-of-stake can replicate the same complex emergent properties, for example, security, scarcity, decentralization of control, etc., as proof-of-work is, according to many, a fraudulent claim. Not surprisingly, the lead developers of the largest proof-of-stake system started a trend of marginalizing those who accuse them of being fraudulent as being Bitcoin maxis, the implication being that people who believe that proof-of-stake systems cannot claim to be decentralized or cannot have the same complex emergent behavior as proof-of-work protocols are closed-minded. This behavior of claiming that imaginary power can have the same properties as real power could be interpreted as precisely the same style of God-King abstract power building, which motivates entire populations of people to willingly forfeit their real power for systemically exploitable imaginary power, because they don't understand the complex physical and systemic differences between real power and imaginary power-based resource control structures. It even has the same moral, ethical, and ideological motivations behind it. People who forfeit the use of proof-of-work protocols like Bitcoin in favor of proof-of-stake protocols like Ethereum are explicitly forfeiting their capacity and inclination to project physical power and impose severe physical costs on attackers, because they're ideologically inclined to believe that Bitcoin's power expenditure is bad. This, of course, creates a window of opportunity for systemic predators to prey on these ideological beliefs, to convince the general public to forfeit proof-of-work protocols like Bitcoin in favor of alternative protocols where a select few anonymous people have systemically exploitable administrative permissions and control authority over the system via their large and physically impossible to verifiably decentralize amount of so-called stake. Just like they have been doing for thousands of years, people want to believe that proof of imaginary power protocols can sufficiently replace proof of real power protocols, because they don't like the energy expenditure required to use real power as the basis for settling their disputes, establishing control authority over their valuable resources, or achieving consensus on the legitimate state of ownership and chain of custody of their property in a zero-trust, permissionless, and systemically secure way. As a result of this desire not to use physical power, we can see the exact same security vulnerabilities discussed at length in the previous chapter. People who are adopting proof-of-stake systems are adopting trust-based, permission-based, inegalitarian, and systemically insecure imaginary power hierarchies. History tells us what happens to these systems. They eventually become dysfunctional, as the people with the most abstract power and control authority over the system start to abuse it, and users are incapable of stopping it because they made the mistake of believing that encoded logical constraints would secure them. Section 5.10.3 The change from Ethereum 1.0 to Ethereum 2.0 created a huge systemic security vulnerability. One of the ways that I like to think about this in a more philosophical way is like proof of work is based on the laws of physics, so you have to sort of work with the world as it is. You have to work with electricity as it is, hardware as it is, what computers are as it is. Whereas, because proof of stake is virtualized in this way, it's basically letting us create a simulated universe that has its own laws of physics. And that gives us, as protocol developers, a lot more freedom to optimize the system around actually having all the different security properties that we want. If we want the system to have a particular security guarantee, then often there's a way to modify the upper state mechanism to also achieve it. Vitalik Buterin, the night of Ethereum's transition from proof of work to proof of stake. This section will repeat many of the concepts from the last section, but apply them more specifically to the context of the Ethereum computer network, which is currently the most widely adopted proof-of-stake network. This section summarizes arguments that have been made against the Ethereum network, most notably the argument that Ethereum developers are fraudulently claiming to be able to achieve the same level of security and decentralization as the Bitcoin network, while eliminating the energy expenditure of proof of work. If the reader isn't interested in learning more about these arguments, they are encouraged to skip this section, as it repeats many of the concepts presented in the previous section. As discussed in section 5.4, a primary challenge associated with cybersecurity is a lack of the ability to apply physical constraints to software. Another challenge associated with cybersecurity, outlined in detail in section 5.4.6, is that because software is abstract, computer program developers use arbitrary and semantic metaphors to describe their software designs that are not technically accurate and often disguise critical information needed to understand how secure that software is. This is a systemic security vulnerability because it creates a window of opportunity to, sometimes intentionally, design exploitable design features into a given piece of software, and then disguise those security vulnerabilities with disingenuous metaphors. The author argues that this is what has occurred with Ethereum's recent pivot from a proof-of-work security protocol to the proof-of-stake security protocol. After making this change, Ethereum developers are fraudulently claiming that stake, aka abstract power or rank, can provide the same systemic security properties as work, aka real power or watts. Using the concepts of power projection theory presented in this thesis, we can see that during the conversion from Ethereum 1.0 to Ethereum 2.0, developers converted their software from a physical power-based resource control system, constrained and secured by physics, to an abstract power-based resource control system, with no physical constraints or thermodynamic restrictions, thus dramatically changing the software's complex emergent security features, and giving unimpeachably consolidated control authority over the system to Ethereum's largest owners. Ethereum's most famous co-developer, Vitalik Buterin, asserts that their decision to remove physical constraints is actually good for cybersecurity, because it enables Ethereum's developers to use encoded logical constraints to logically secure the system, rather than using energy-intensive physical costs, aka watts, to physically secure the system like proof-of-work protocols do. Buterin's assertion not only contradicts decades of established principles in system security, it's also blatantly illogical, as 1. It is obviously physically impossible for encoded computer logic alone to fully replicate the emergent benefits of physical constraints, and 2. Computer logic alone is demonstrably incapable of preventing the systemic exploitation of computer logic, hence every software hack that has ever occurred. By changing from a proof of work, aka proof of real power, security system to a proof of stake, aka proof of imaginary power, security system, not only has it become physically impossible to verify that Ethereum is a decentralized system, it has also created another type of software-defined, abstract power-based resource control hierarchy, which gives extraordinarily asymmetric abstract power and control authority over to an anonymous group of people who control the majority supply of stake. Ethereum users must necessarily trust that people who control the majority supply of stake will not exploit or abuse it, and they are counting entirely on systemically exploitable encoded logic, which they write, to secure users from exploitation and abuse, because users are now physically powerless to secure themselves using physical power. To illustrate the systemic changes which occurred when Ethereum changed from a proof-of-work system to a proof-of-stake system, Figure 86 provides a side-by-side comparison between the control structure model of a proof-of-work system and a proof-of-stake system. The reader should note that these are the same control structure models discussed in section 4.7. Here we can see that proof-of-stake creates a near-identical resource control structure as proof-of-work that is easy to misperceive as the same system. The controlled process, in this case the bits of information recorded on the blockchain, is the same, the controllers are the same, and the general structure is the same. The main difference is simply the type of power used. Whereas Ethereum 1.0 was a physical power-based resource control hierarchy that utilized real power, aka watts, Ethereum 2.0 is an abstract power-based resource control hierarchy that utilizes abstract power, aka stake. As introduced through the concepts of power projection theory presented in the previous chapters, it's easier to spot the systemic differences between Ethereum 1.0, a proof-of-work system, and Ethereum 2.0, a proof-of-stake system. Ethereum 2.0 is far more vulnerable to systemic exploitation from those who control the majority supply of Ether, whereas Ethereum 1.0 isn't. This exact same principle also holds true for other proof-of-work systems like Bitcoin. Bitcoin is not nearly as systemically vulnerable to users who have the most Bitcoin, because owning Bitcoin doesn't give users the same type of special administrative privileges over the system, namely validation rights, as people's Ether give them in the Ethereum 2.0 control structure. Another way to illustrate this systemic security flaw is to revisit the threat posed by domestication. From a functional perspective, proof of stake is a repeat of the domestication hazard discussed in sections 3.10 and 4.8. By switching from proof of work to a proof of stake system, Ethereum users have allowed themselves to give control authority to people with abstract power rather than those with real power, aka watts. As a result of making this change, users tacitly forfeit their ability to gain and maintain special administrative privileges, namely validation rights, over the system in a zero-trust, permissionless, and egalitarian way that can be verifiably decentralized simply by projecting their own real power. People who forfeit proof-of-work systems for proof-of-stake systems are forfeiting their own capacity to tap into an unbounded supply of non-systemically exploitable physical power, which they could use to impose severe physical costs on other users who exploit or abuse their special administrative privileges. Consequently, the BCRA of exploiting the special permissions granted to users with stake will only increase, because it's physically impossible for users to increase their cost of attack. A leading cause of people's confusion about the difference between proof of stake and proof of work is that they don't understand the physical and systemic differences between what people arbitrarily call work and what people arbitrarily call stake. The key insight that people are missing is that work refers to real-world physical power, aka watts, whereas stake is an arbitrary semantic expression given to an imaginary object-oriented software abstraction. This subtle but key difference has important implications because it means that proof of work and proof of stake systems are incontrovertibly different technologies, down to the base layer state mechanism, making it physically impossible for proof of stake systems to replicate the same cybersecurity properties as proof of work systems. Most notably, the ability to keep special administrative privileges physically decentralized and unimpeachable. If stake doesn't physically exist, then that means it's physically impossible for the special administrative privileges granted to proof-of-stake protocols to be decentralized anywhere except exclusively within people's collective imagination. The author is being repetitive because this is a crucially important concept to understand that clearly isn't resonating with the general public. Therefore, the key to understanding the systemic security flaw of proof-of-stake systems like Ethereum 2.0 is to simply recognize that stake doesn't physically exist. Stake is purely an abstraction, a name that developers intentionally made up to obfuscate who has access to the special administrative privileges needed to approve or disapprove transactions, which is most likely centralized amongst the Ethereum Foundation and large investment institutions. Anybody who uses Ethereum 2.0 tacitly requires validation, permission, and approval from these administrators who have abstract stake, aka rank or abstract power. If these anonymous people choose not to validate a user's valid transaction request, then a user's ability to utilize the blockchain will be degraded. As of this writing, 60% of all transactions that have been made on Ethereum 2.0 have been compliant with sanctions imposed by the Office of Foreign Assets Control, OFAC. In other words, 60% of all valid but non-OFAC compliant transaction requests have been deliberately censored by those who have special administrative privileges granted to them by their stake. Thus, almost immediately after switching from proof of work to proof of stake, Ethereum became a majority censored blockchain, where valid users requesting valid transactions, who happen to not be OFAC compliant, are being denied 60% of the time. Clearly, these people's ability to utilize the blockchain has been degraded in comparison to other users, and there is little they can do to eliminate the degradation. According to Ethereum's developers, this type of degradation shouldn't occur, because validators should know that degrading people's access to the blockchain decreases the value of the blockchain, yet the attacks are still occurring. Also, according to Ethereum's developers, users have the ability to slash the stake of validators if they censor transactions like this. Yet, to date, none of the validators who are censoring non-OFAC compliant transaction requests have had their stake slashed, because to do so would require users to come to consensus via a voting system that stake should be slashed. As always, the problem with voting systems is that voting systems represent yet another form of trust-based, permission-based, and inegalitarian abstract power hierarchy. Those who are having their transactions degraded have no ability to project power on their own in a zero-trust and permissionless way to take back the administrative privileges that are being used to degrade them. They are wholly reliant on voters. Recalling the core concepts from Section 4.6 on creating abstract power, to seek permission or social approval from someone, particularly software administrators, is to tacitly give them abstract power over you. On the flip side, if you want to create and wield abstract power over a large population of humans, simply convince them to adopt a belief system where they need permission or social approval from you. Once a population has adopted a belief system where they need your permission or approval, which you can trick them into adopting by obfuscating the permission-based control hierarchy, you have successfully gained abstract power and influence over them. This is what proof of stake does. In direct contrast, proof of work systems give these special administrative permissions freely to anybody willing to solve its proof of work algorithm, not those who own Bitcoin. Because the work expended to solve this algorithm is a physically real phenomenon, work refers to real power, aka watts. That means the special administrative permissions of the Bitcoin network can 1. Be physically impeached or countervailed by any user of the network for any reason at any time by simply overpowering them with more hash, and 2. Be physically decentralized across the planet. Neither of these important emergent properties are true for stake. Despite the fact that stake doesn't physically exist, people claim that administrative control over Ethereum 2.0 is decentralized. Here, the word decentralized is used in quotes to remind the reader that an abstract software object like stake, which doesn't physically exist, cannot be verifiably decentralized because stake isn't a real thing. Since stake is purely an arbitrary semantic description of an abstract object, that means the special administrative permissions given to Ethereum 2.0 validators can only be decentralized in name only. The following point demands to be repeated because the general public doesn't seem to understand this. It's physically impossible to prove that the special administrative permissions given to those with stake is decentralized, or conversely, that it wasn't already centralized from the very start, because stake doesn't physically exist. The only place that Ethereum's stake can be decentralized is in people's collective imagination. Ethereum's developers claim that stake is decentralized because it has been divided across different validators. However, logically partitioning stake across different addresses or validators doesn't mean those addresses or validators aren't controlled by the same person or group of people, groups like the Ethereum Foundation. So it's impossible to claim that stake is decentralized, merely because it has been mathematically partitioned across multiple addresses or across multiple validators. The same person could easily control millions of validators, and the fact that validator node hardware has a minimal physical signature actually makes it easier for people to disguise how many validators they own and control. This highlights another baked-in security feature of Bitcoin's hashing infrastructure that some might not appreciate. The fact that Bitcoin's hashing infrastructure consumes so much energy gives it a large physical footprint that's much harder to hide or disguise, thus harder to centralize under one person or organization's control. In other words, the more power that Bitcoin's hashing infrastructure consumes, and the more heat that it produces, the easier it is for people across the world to independently verify that it's decentralized. On the contrary, the fact that Ethereum 2.0's validator network consumes so little energy makes it far easier to obfuscate how centralized the special administrative permissions coupled to stake is. The lack of Ethereum's electricity consumption essentially functions as a cloaking or stealth mechanism for people or groups, for example, the Ethereum Foundation, to disguise how much abstract power and validation authority has been consolidated under their direct control. It's already public knowledge that the majority of stakeable Ether was awarded to Ethereum 1.0's founders before it was released to the public. Combining this fact with the fact that stake doesn't physically exist, this means nobody can verify that Ethereum 1.0's founders don't already have the majority of Ethereum 2.0's stakeable Ether. If nobody can verify that Ethereum's founders don't already have the majority of stakeable Ether, this means nobody can verify that Ethereum 1.0's founders haven't already consolidated majority control over Ethereum 2.0's special administrative privileges. So not only is it physically impossible to verify that stake is decentralized, there's no indication to believe or verify that Ethereum 1.0's founders don't already have unimpeachable centralized control authority over Ethereum 2.0. To make matters even more systemically vulnerable, Ethereum 2.0's staking protocol is designed so that people who have more stake are rewarded with proportionally more stake, and those rewards are compounding. This is an extremely noteworthy design feature. Ethereum 2.0's developers deliberately added additional design logic into the system which gives the people who have the most stake the most rewards. In other words, the protocol is intentionally designed to give the people who already have the most abstract power even more abstract power than anyone else in the future. The more stake they control today, the more stake they will get to control in the future. The emergent effect of this design logic is that the people who have the most abstract power and control authority over the system today get to keep it forever. Not only that, but the abstract power also grows and consolidates as a higher percentage of the system's total stakeable ETH is gradually awarded to them because of the protocol's compounding reward system. The author has now highlighted 5 systemic security vulnerabilities associated with Ethereum's conversion from a proof-of-work system to a proof-of-stake system that are quite easy to recognize. First, proof-of-stake causes people to forfeit their ability to impose severe physical costs on attackers, effectively domesticating users. Second, proof of stake is decentralized in name only, because stake doesn't physically exist, and therefore can't be verifiably decentralized. Third, validator hardware has a minute physical signature, making it easy to hide centralized control over validators. Fourth, the system is intentionally designed to give the people with the most stake today the most stake in the future, thereby consolidating, in other words, centralizing, stake into the hands of the people who already have the most stake. Fifth, it's already public knowledge that the people with the most stakeable ether are probably the people who awarded themselves with the most ether when they originally developed the software, and there's no way to verify they don't continue to have it. Ethereum 2.0 is therefore a decentralized in name only (DINO) abstract power hierarchy. Users who accepted the conversion from Ethereum 1.0 to Ethereum 2.0 have adopted yet another belief system that gives people asymmetric and consolidated abstract power over them, and then trusts them not to exploit or abuse it. By coupling special administrative privileges needed to approve transactions to those who have the most stake, a proof-of-stake system removes all of the physical constraints that were keeping those special administrative privileges physically constrained and physically, thus verifiably, decentralized. Now, the people who have the most stake have the critical administrative privileges to approve transactions, but that stake is completely imaginary. Switching from proof of work to proof of stake effectively functions as a way to change and then obfuscate which group of people have the most important administrative privileges and control authority over the system. People buy into this sleight of hand because they don't understand enough about the complexities of computer theory to understand that stake doesn't physically exist and is purely an object-oriented abstraction for what could also be called rank or admin rights. In other words, stake is nothing more than a metaphor for abstract power. People with the most stake have the most administrative privileges to approve or disapprove transaction requests. Thus, they wield substantial abstract power. Moreover, we already know that the people who probably have the most stake are Ethereum's core group of developers and co-founders, since they overtly awarded themselves the majority supply of stakeable ETH several years ago, and they can't prove they don't still control it. This concept is illustrated in Figure 87, Software Administrators with Stake in Ethereum 2.0. Not surprisingly for anyone who understands power projection tactics in human society, Ethereum developers will argue that Ethereum 2.0 is still systemically secure against exploitation because of the systemically exploitable voting logic, aka slashing, encoded into the software that will ostensibly prevent them from abusing the special authorities given to them by their stake. Users must assume that staked ETH isn't already majority controlled by one organization to believe that the voting logic for slashing belligerent stakers will work as intended, which is a blind and unverifiable assumption. Here we have a situation where the people who gave themselves the most abstract power are claiming that users can hold them accountable by slashing their abstract power using a systemically exploitable voting system that they encoded. This would be yet another situation where the people with abstract power try to convince their believers that a belief system is secure against systemic exploitation because of systemically exploitable logic that was encoded into the system to constrain abstract power by the people who have the most abstract power. Remarkably, despite literally thousands of years of written testimony from history, discussed at length in section 4.8, to show that design logic, especially voting systems, can't secure a belief system against the exploitation of logic, people accept this argument.